Okay, let me talk about the interquartile range first. Or maybe just go in the order of the book. Let's see what the book presents first. Here you have dot plots. Yeah, the first one is the easiest one, the range. Range is one of the measures of central tendency. The only thing you have to do to calculate the range is to do the biggest number minus the smallest number. That gives you the range of your sample. So for example, if you have a set of data like here in this set, you find the biggest number. The biggest number seems to be 42, yes, minus the smallest number, which is 38. So 42 minus 38, that's 4. That would be the range of the data set. Or maybe the biggest one was 43. I didn't see that. Yeah, there's 43 here. So 43 minus 38, that's the biggest number, minus the smallest number, 38, 38, it's going to be 5. That's the range. Let's talk about variance and standard deviation. So the formula for standard deviation is like this. So these are, you have the formula for the sample variance. This formula here is just the same as this formula, but it's easier computationally, it's easier to use. And if you take root of your sample variance, you're going to get your standard deviation. So root of variance is going to be a standard deviation. So let's just do the calculations using a set of data. I'm going to create maybe just use a simple set of data like set 1 over here. Yes, so this set, we have 40, 38, 38. So this is my data. 40, 38, 42, 40, 39, 39, 43, 40, 39, 40. So I want to calculate x bar, s squared, and s for this data. So I'm going to use this formula because it's computationally easier. Yes. So what do I need for this formula? I need sigma x squared. So I need sigma x squared. And I also need sigma x. I need sigma x. And what else do I need? I need n, which is the sample size. In this case, the sample size is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers. So n is 10. So what is this? This is called the sum. You just need to add them all up. Yes, you add them all up using a calculator. And if you do so, do I have, okay, I'm going to just use a calculator to add them all up. 40 plus 38 plus 42 plus 40 plus 39 plus 39 plus 43 plus 40 plus 39 plus 40, 400. Okay. Then we need something called sum of squares. And what does that mean, sum of squares? You need to square each one of them and add them up. That is, you have to just do the first number 40 squared plus the second number 38 squared plus, and you keep adding them up until the last one. The last number is 40 squared. So this is called sum of squares because you square each one of them and you add them up. Yes. So I'm going to do that with this calculator. 40 squared plus 38 squared plus 42 squared plus 40 squared plus 39 squared plus 39 squared plus 43 squared plus 40 squared plus 39 squared plus 40 squared. I get 16,020. Okay. Then, in order to calculate s squared, I'm going to use this formula. So s squared is the sum of the squares minus the sum to the power of 2 over n minus 1. So it's going to be 16,020 minus the sum, which is 400 squared, over n, which is 10 over 9. I need to calculate that. That's going to be okay. I need braces, so I'm going to go to the scientific calculator so that I can use braces. So I'm going to open a brace, 16,020 minus, I'm going to open another brace, 400 squared divided by 10 close that brace, close that other brace as well, and then divided by 9. So it gives me 2.222 forever. My standard deviation is going to be a root of 2.222 forever. So if I take root of that, it's going to give me 1.491107. So that would be my standard deviation. Any questions about how we use this formula? You need to just find the sum. You need to find the sum of the squares, and then you plug them into the formula. You're good? Okay. What if you're dealing with the population? If you're dealing with the population, not with a sample, then you can calculate the population variance. And you can calculate the population standard deviation. The only difference is that at the bottom, rather than having lowercase n minus 1, you have just n. So you see the difference between the formulas? For sample variance, for sample variance, the formula is sigma x squared minus sigma x to the power of 2 over n minus 1. But for population variance, and you can calculate population variance only if you have the measurement for all the individuals inside your population. That's going to be sigma x squared minus sigma x squared over n. And at the bottom, you also have n. You don't have n minus 1. Are we good? Or this one can also be written as sigma x minus x bar squared over n minus 1. And this one can also be written as sigma x minus mu squared over n. But again, using this would be easier computationally. You just need to figure out what the sum is, what the sum of squares is, and then you plug in the values. This formula is rarely used because in most cases you're dealing with a sample and you don't have the measurement for all the individuals inside the population. So you're mostly dealing with a sample, and you will be using this formula to calculate the sample variance. Any questions? Okay. Now that you know about the mean and you know about the variance, here you have some diagrams that compare different scenarios. So imagine you have two sets that have the same variance and they have the same mean. If the mean and the variance are exactly the same, then they're going to be identical. They just, one is on top of the other one. These are the relative frequency histograms. Another scenario is if you have two sets and these two sets have the same variance. If they have the same variance but different means, so you can have a bell like this, and here the middle you have the mean of the first population, and imagine that the mean of the second population is bigger. However, the variances are the same. If the variances are the same, then you're going to have a situation like this. When you compare the two, you will see that it's like a shift. The red one is going to be just like the blue one, but shifted to the right because it has a bigger mean. But the shape of the curves will not be different. Their shapes will be the same. Make sense? And in this one here, you have a situation where the means are the same. So these two populations, they have the same mean. One could be, for example, the height of, let's say, students in one school, and the other one is the height of the students in another school. If they have the same mean, but imagine that the standard deviation in the second school is bigger than the standard deviation in the first school. Yes. Then this is going to happen. From the first population where a standard deviation is a small, you're going to have a tall curve. But if the standard deviation is big, it's going to be more spread out. Yes. So this represents population 2, and this one represents population 1. They have the same mean. That means the middle of the data is the same. X1 bar is equal x2 bar. Middle is the same. But the second population is more varied, the variance is higher. So the variance is bigger. So it's more spread out. As you can see, it's more spread out. But in the first population, the variance is small, so variety is lower. So they're all gathered around the mean. So this one will be tall and narrow. This one will be tall and narrow, but this one will be short and wide, which represents a bigger variance. And the last one is a situation where the blue one has a bigger variance. It also has a bigger mean. And the red one has a smaller variance. And as a result, it's narrower. It also has a smaller mean. So it's shifted to the left. Are we good?